Welcome back to Psychology 1. This will begin the first of our lecture video series for this course. This material that we're going to cover today will correspond to Chapter 2 in your textbook, covering critical thinking, research methodology, and research ethics. But first, before we launch into the slides, I want to give you a little bit of background. I want you to understand why this is so important to me and to psychology in general. I want you to be a skeptical, excellent critical thinker. I want you to not trust information that you're given in media, whether it's a website or a news program, whether it's an article that you're reading, even a book that you've picked up to read, and whether it's about mental health or the effects of media on children, you name it. I want you to look at all that data, even if it's published in a scientific study, and I want you to question it. 20 years ago, a study was published suggesting that MMR vaccines, measles, mumps, rubella vaccines, caused autism. It was published in 1998, and about 4 years later it was retracted because it was found that the author had falsified that data. This has unfortunately had a real-world impact. Parents are choosing not to vaccinate their children because they believe in that study. They are convinced that vaccines are harmful. I will tell you that 1 in 60 children that gets measles will die. 1 in 300 in countries that have the best quality medical care will still die. The risk for children with measles far outweighs any potential minor side effect like an allergic reaction or a febrile seizure that a child might have, and there is no evidence showing that MMR vaccines have any other negative side effects. But parents are convinced. Parents are also convinced that sugar makes their kids hyperactive. I want you to be skeptical when you hear things like that, and I want you to ask, where's your data? Show me a study that shows that that's actually an effect. Because in fact, there is no data out there that supports the idea that sugar makes kids hyperactive. In fact, as I will tell you later, there's evidence showing the reverse, that sugar actually helps adults concentrate better on tasks when they're stressed. But more on that later. For today, let's talk a little bit about our lecture material. So, to kick off our lecture series, I want to introduce you to the format of all of these lectures. You're going to find that the first slide of all lectures will be a learning outcome slide that will tell you the 3 goals that I have for you by the end of this class. So, by the end of today, you should be able to describe the 3 goals of psychology. You should be able to discuss the meaning of the terms theory, hypothesis, and variable. Lastly, you should be able to contrast the 3 major types of research methods that are used by psychologists and the ethical principles that guide research in psychology and other fields. Let's start by talking about what is psychology. You may have a definition from the book, or you may have your own personal definition. Pause the video here and write down, what is your definition of psychology? Is it an area of study? What do we study? Maybe we study the brain. Maybe we study people. Maybe we even study animals to learn more about people. In general, you might come up with something like, psychology is the scientific study of the brain, the mind, and behavior. The brain is sort of the physical structure composed of chemicals, cells, neurons, astrocytes, and other kinds of matter. The mind, oftentimes people think of as the thought processes and the emotions and feelings. And it used to be that we thought of the mind and the brain as 2 separate entities, that your brain was the physical structure and the mind was the thought process. But nowadays, we really think of those as one and the same. The brain is the physical structure, but that interaction of chemicals and electrical signals and cells produces those thoughts, feelings, and behaviors. So really, I want you to think of the mind and the brain as the same thing. Scientists also study behavior, right? The motor actions that we do that tell us something about what's going on with an individual. Do we measure anxiety with behavior? Do we measure depression with behavior? Behavior becomes centrally important in a great deal of psychological research. But why? Why are we interested in studying the brain, the mind, and behavior in humans or in animals? Well, in general, psychology has 3 goals. First, we want to measure and describe the natural world. I want to really know what's happening out there. What are people thinking and feeling, right? I just want to describe what's going on. And that's really where all sciences started, was just trying to describe the natural world. But quickly, they often advance to looking at understanding and predicting the causes of events. In this case, maybe the causes of behavior. Because if we can predict the causes of behavior, that allows us to reach the third goal, which is application of research findings. So if we understand the causes of gun violence in society, if we understand the causes of mass shootings, if we understand what causes violence in young children, we can then start altering their environment to help reduce some of that violence or mass shootings. In addition, if we understand what causes clinical depression, then we can use those research findings to help people. If we can understand the causes of divorce, then we can intervene early in marriages to help to prevent divorce. As we'll talk about in our next lecture, we know a lot about actually many of these things, such as aggression and divorce, and we actually can reverse some of those harmful effects already. But the way that we're going to describe the natural world, understand the causes of events, and then apply those research findings really relies on the scientific method. The scientific method is an organization of how we think about the natural world in any science, not just social sciences, but physical sciences and life sciences. The scientific method requires that we systematically identify the variables that we're interested in measuring. A variable would be any measurable event, characteristic, or behavior that we're interested in trying to understand. For example, if I want to know what factors help student performance, and I'm thinking about student performance, I need to define what I mean by student performance. Am I talking about exam scores? Am I talking about a grade in a class? Am I talking about your grade point average? Or maybe I'm just interested in whether or not you graduated from college or you're going to graduate from college. All of those might be measures of student performance, but the kind of question that I'm interested in understanding will tell me which of those measures is the most valid or the most useful for my study. Once I've identified my variables and I understand what I'm looking at, then I might generate a hypothesis. Now, for many of you in 7th grade science, you probably heard that a hypothesis is a theory that's not been tested. This is wrong. A hypothesis is a precise, tentative statement about the relationship between two or more variables. But really, it is specific. It is, I think, that the more sleep you get, the better you're going to do on exams. What are my two variables in that hypothesis? Sleep, exam performance. Hopefully that's what you said. But the question is, what do I mean by sleep? Am I talking about hours of sleep? Well, at some point, if you're getting 12 or more hours of sleep, that's probably not helping you much. So I might have to define that variable more specifically. What I think is that if you get more than 6 hours of sleep a night, your exam performance goes up. Whereas if you get less than 6, that you're not going to do as well. Now again, just a hypothesis, right? But we could test that. And the idea about a hypothesis is that it's testable, and you can then either refute it because you found evidence that did not support it, or you found evidence that did support it, and then you would use that hypothesis in future studies. But over time, with many studies, you may develop a series of hypotheses, not just about exam performance and sleep, but about exam performance, GPA, sleep, social environment, unit load, workload, and all the factors that help students to be successful in school. That might lead you to generate a theory. A theory is a broad set of closely related ideas that can explain many observations. So a theory is made up of multiple hypotheses. It's not just about whether sleep affects your performance on a test, but it's really about what's going to help you to be successful in college, what's going to help you to graduate and get good grades and get a job afterwards. And I might believe that sleep is one facet of that, but in fact it probably also depends on how many units you're taking, how many hours you're working per week. Do you have family support? Is your family encouraging you and helping you to go to college? Do they give you financial assistance when they can? Or even if they don't give you financial assistance, do they give you emotional and social assistance? They're supportive research tells us that all of that actually feeds into student success. All theories must be testable because we need to be able to determine if the theory needs to be thrown out because it's been refuted or whether it's been supported. Very few theories ever stand the test of time as they were originally proposed. Charles Darwin's theory of natural selection is very different than the current theory of natural selection that we use in everyday practice, because over the last 150 years, we've tested and retested all of those ideas and modified that theory to make it a better theory, the theory that it is today. In addition, theories are huge. They're never tested in a single research study. Actually, evidence is accumulated across multiple studies to either support or to change or clarify a theory. I want you to be suspicious of single research studies. If somebody tells you that autism is caused by vaccines, I want you to ask for research studies. Show me evidence. And then I want you to say, I have an alternative explanation. I think it's something else. I think we're better at diagnosing autism now, which is why the rate of autism has gone up in the last 30 years. When psychologists are interested in testing variables and they're going to test a hypothesis, they have a variety of data collection techniques available to them. They might use observation, where they're measuring motor behaviors, so they're just observing what people do. If I want to measure romantic love, I might actually just watch how do couples interact together. Do they kiss? Do they hold hands? Are they affectionate with one another? Do they spend a lot of time touching, or are they in close contact with one another? All of those would be motor behaviors that might tell me something about romantic love. But observations sometimes take a significant amount of time. It might take me hours of observing a couple to really know for sure whether or not they're in a romantic relationship, rather than just on a date, for example, or maybe just really close friends. So I might use a survey or an interview. I could just ask them, are you together? How do you feel about each other? Would you sacrifice for the other person? Do you live together? Right? I might ask a series of questions about their attitudes, their beliefs, and their behaviors to understand whether they are in a romantic relationship. But while surveys and interviews tend to be faster than observations, they allow you to collect more data, they also suffer from a significant problem. People lie on surveys. They want to cover up things they don't want you to know about or that maybe they're embarrassed about. Now, in psychology, we don't call it lying because we're nice. We actually call it the social desirability effect. The social desirability effect is the idea that people want to tell you what you want to hear or what they think you want to hear when they're giving you answers on a survey or an interview. Another technique we could use is a psychological or standardized test. So we might look at a standardized test given to hundreds or thousands of people to measure differences in ability, such as personality, intelligence, career choice, or aptitude. As you're all familiar with, you've had a career of taking standardized tests if you've been in education for any significant length of time. You've taken them every year, either as part of K through 12 education or in other settings. These allow us to look for differences amongst groups of people and potentially to intervene if we want to help people. We want to help them do better in the classroom, or if we're going to hire someone for a job, we might look at their personality traits to determine if we think they're going to be suited for that job. Lastly, psychologists might use physiological measurement. These would be things like measuring brain or body activity, hormone levels, heart rate, brain size, and brain chemicals. Most of these are pretty new. We've been able to measure heart rate and some basic brain chemicals like adrenaline for a while, but really in the last 20 or 30 years, we really advanced in what we can measure. We can measure stress hormones in your saliva. We can measure brain chemicals actually in your brain. We can do an MRI or a CAT scan to measure brain size. We can do other kinds of brain scanning techniques to identify brain activity. So we really do have a host of things we can measure in psychology. Psychology has 3 research methods they use to understand the natural world. The first one is descriptive research. Descriptive research describes characteristics of a group in the real world, such as Jane Goodall, pictured here on the slide, observing chimpanzees in Gombe, Africa. Jane Goodall was one of the first people to observe chimpanzees in their natural environment, to observe their natural social structure and what they tended to do in groups. 1971, it's only recently that we've gained some of the information that we now know about apes and other primates because of pioneering work by Jane Goodall and women like her. Descriptive research doesn't have to involve animals, though. Psychologists use it all the time. They go into people's social environments, classroom settings, work environments, and just observe how do people study, how do they interact in groups, how do they socialize with others. It tells us something about how people behave. Now, this study might involve a large group of people, like chimpanzees and Gombe, or it could involve a small group, in some cases as few as one individual. That would be a case study. We're going to come back to case studies and talk about them on the next slide, but descriptive research can involve any number of individuals. One of the problems with descriptive research, as with any research, is that you might have a sampling bias. Your participants might not be representative of the population that you're interested in. Let me give you an example. I'm a psychologist interested in the study habits of students when they're on campus. So I go to the library and I observe how are students studying. How much time are they looking at their book? Are they taking notes? How long are they looking at their phone? Or are they interacting with friends? How often are they on social media? All of those might go in to give me an idea about how efficient students are using their time. Except for not all students go to the library, right? If you're working and you have to work right after class, you probably don't have that time. And if you are working right after class, maybe you're more efficient at organizing your studying. So when you do have time to study, maybe it's not at school, but it's at home, and I wouldn't be able to observe your study habits without being a little bit creepy. Okay, so sampling bias is not just a problem of descriptive research, it is a problem that could happen in any kind of research. And psychologists tend to suffer from this problem pretty significantly. About 80% of all research in psychology involves undergraduate students, college students, who are in introductory psychology courses. The problem is that psychology students don't look like the rest of the population. Psychology students are in college, first of all. That's a subset of the population. They tend to have higher IQ, they tend to have a better income. There are many ways in which psychology college students look different than the rest of the population. So sometimes we can't prevent sampling bias, but we can be aware that it might be altering our results. Another problem that is only found in descriptive research is that descriptive research cannot actually test a hypothesis. Because you're just observing individuals in their natural environment with no attempt to manipulate variables or to change the environment, you're really not able to test a hypothesis. So I mentioned earlier that we were going to go and talk about a case study. So case studies are a kind of descriptive research involving a small number of individuals. Let's take a look at that. A case study examines a single case or a limited number of individuals in great detail, such as investigating what makes the Dalai Lama who he is. So the Dalai Lama is a religious and political leader who was selected at birth to take that position. This is unlike almost any other position in the world. So you might be interested in these psychological effects of being raised to be a leader from birth. And you might use the Dalai Lama as a case study to investigate what are the psychological effects of that. But it's not just used to investigate religious or political leaders. It's also used sometimes to investigate accidents or rare events. This pictured here is Phineas Gage. Phineas Gage was a railroad supervisor in the 1800s. You can see that his eye is closed. Unfortunately, he suffered from a major trauma where an iron rod was shot through the back of his skull, or through the back of his cheek, up through the top of his head. So Phineas Gage was a railroad supervisor who was using a 3-foot-long iron tamping rod to pack gunpowder into a rock. He unfortunately sparked the gunpowder, which then blew the rod through the top of his skull. Pictured here, you can see a computer reconstruction of where the rod probably passed. It went behind his eye and out the top of his skull through his frontal lobe. This became a case study about the effects of brain trauma on the frontal lobe because Phineas Gage, after the accident, suffered from a series of psychological changes. He became aggressive, an alcoholic, very impulsive, had lots of get-rich-quick ideas and would spend all of his money very quickly, wasn't able to save it. So his wife and his physician reported all of these behaviors. He was followed up until his death. And it became the foundation for our understanding that, well, maybe the frontal lobe, pictured here, is involved in impulse control and regulating those initial impulses and thoughts and alcohol consumption and aggression. But there's a problem with case studies. Remember, in this case, you've only got one individual, and even in the best case studies, you only have a small number of participants. And we don't really know why Phineas Gage changed. Yes, it could be, like the researcher suggested, and like his physician suggested, that Phineas Gage is different because of brain trauma, that his frontal lobe was important in regulating impulses, and once it was damaged, he was no longer able to do that. Alternatively, though, it could just be that he had trauma and post-traumatic stress disorder. Maybe he changed because he's disfigured and he suffered a significant amount of pain and damage. Remember, it was the 1800s. There was no antibiotics. There's no real treatment available to him. There's a small amount of pain medication that might have been available, but there's no real recovery for this. It could also be that it was the infection because he got a fungal infection and fell into a coma for 30 days after the accident. They thought he was going to die. He did happen to wake up, but that was a shock to his doctors and to his wife. The other thing is maybe he was always like this. Maybe he was always an aggressive alcoholic, but his wife and he had an excuse to be able to use after the accident to say, oh, it's a lot worse now. But we don't really know, right? We're relying on their reports of his behavior. And you might notice his alcohol consumption now that he can't work anymore and he's home all the time, when maybe he consumed the same amount of alcohol even before the accident, but maybe his wife just wasn't paying attention to it as much. That's the problem with case studies. We can never really know what caused his behavior to change. In fact, if we want to try to investigate the potential causes, we need a kind of research method that's a little bit more advanced. In this case, we're going to look at non-experimental, or what your book calls correlational research. Non-experimental research examines how two variables are related without any attempt to change them. Okay? So, in the Phineas Gage example, if I think that the frontal lobe is involved in regulating impulse control, I need to look at a group of people that have different frontal lobes without me going in and damaging them. And unfortunately, there is that group of people. People who ride motorcycles are at a higher risk of coming off the front of their bike and damaging their frontal lobe, even when they have a helmet on. So, we might look at two groups of individuals, both who ride motorcycles, one who's come off the front of their bike and damaged their frontal lobe, and another one that also had an equally bad accident, but maybe didn't damage their frontal lobe. Maybe they damaged a different side of their brain. That might allow me to then compare their brain damage to their impulse control, and I might use standardized measures of impulse control or alcohol consumption or aggression to do a correlational study. Now, if individuals show with frontal lobe damage show poor impulse control, that would suggest that there's a link between the frontal lobe and impulse control. Now, there are many other kinds of correlations we might examine. Another example that's probably more familiar to you is the link between mood and levels of sunlight. Oftentimes we believe that the more sunlight there is, the better our mood is going to be. So higher levels of sunlight or higher amounts of sunlight and higher mood. That would be a positive correlation where both the variables are changing in the same direction. Now, positive here doesn't mean a good correlation. Positive just means that both variables are going up or both variables are going down. So as the level of sunlight goes up, your mood also goes up. As the level of sunlight goes down, your mood also goes down. Both of those would be a positive correlation. But there could also be a negative correlation. A negative correlation is when the variables change in opposite directions. Let me give you an example. The more alcohol you consume, the lower your exam score, right? Alcohol consumption is going up, exam scores are going down. That would be a negative correlation. Again, negative here does not mean bad. It just means that the variables are changing in opposite directions. So the way that we measure the magnitude or the strength of those relationships is using a correlation coefficient. So whether it's a positive or negative correlation, the correlation coefficient can range from 0, which means there's no correlation at all, to 1.0. 1.0 correlation would mean that there's a pretty strong correlation between those variables. And then it either has a positive sign if it's a positive correlation, or it has a negative sign if it's a negative correlation. Okay, Professor Johansson finds that for every diet beverage someone drinks during the day, the likelihood of heart attack increases by 4%. The first thing you need to do is identify the two variables in this statement. Then you have to decide whether the two variables are changing in the same direction or in opposite directions. Pause the video and generate an answer for me. Okay, what were the variables? Did you write down every diet beverage and your risk of having a heart attack? And what direction are they going? More diet beverages means higher heart attack risk. That should be a positive correlation. Let's go on to a second one. Margaret notices that the temperature in her office dropped several degrees from July to December. In a careful review of the budget, she discovers that the company's utility expenses also dropped from July to December. What other variables? What direction are they changing in? Pause the video here. Okay, what are the variables that you got? Temperature dropping several degrees, and utility expenses also dropping in the same time frame. That suggests a positive correlation. I realize they're both going down, but remember, positive correlations occur when the variables are changing in the same direction, either both up or both down. Let's do a third one. Dr. Fontaine finds that for every day a person attends an exercise class, he or she loses 0.5% body fat. What are the variables? What direction do they change? Pause the video here. Every day a person attends exercise class is variable number 1, and that's going up, right? The more exercise classes you attend, and what's happening to your body fat percentage? It's going down, right? The more you attend, the lower your body fat percentage. So that is a negative correlation. Could be that you thought about it as a positive correlation, right? The more exercise you do, the more body fat you lose. But in general, probably most people would consider this a negative correlation. But I could see how you might see it as a positive correlation. Last one. Professor Handel notes how long students attended an exam review session. When the exams are graded, she finds that the longer students spent on a review session, the lower their score on the exam. Okay, what are the variables? What direction are they changing? Pause the video here. So the longer they spend at the review session is going up, the lower their exam performance, going down. That's a negative correlation. Now, one of the things you might be wondering here is, but does that mean that diet beverages cause heart attacks? Does that mean that staying longer at a review session lowers my exam performance because I get confused or something like that? That's probably not the case. And that actually illustrates one of the problems with correlational or non-experimental research. Non-experimental research does not tell you cause and effect. It doesn't tell you whether diet beverages cause heart attacks. And it doesn't tell you whether staying longer at the review session causes you to do worse on the exam. And here's a good example from Tyler Vigen's book. This is the correlation between U.S. spending on science, space, and technology from 1999 through 2009, and that is in red. And then it's got suicides by hanging, strangulation, and suffocation, also from 1999 through 2009. You can see the amount spent is here in red on the x-axis, and then over here on the other axis is the number of hanging suicides. The correlation is very strong. Remember I said correlations range from 0 to 1.0. This correlation here is 0.9978. That's almost as close to 1 as you might be able to get. Okay, but does that mean that the more we spend on science and technology causes people to commit suicide? That seems unlikely. Right? There's probably not a causal relationship there. It's what we call a spurious correlation. These two factors just happen to be correlated together, and maybe it's something totally unrelated. Now let's go back to those examples we were just talking about, and let's look at cause and effect. Diet beverages do not likely cause heart attack risk, right? It's that other factors associated with diet beverage consumption are associated with heart attacks. Maybe if you drink diet beverages, you feel like you don't have to exercise as much. Maybe it's that when you drink diet beverages, you feel like you can eat in unhealthy ways in other areas, like with saturated fats or high amounts of protein or other things that might potentially be harmful for you. Similarly, Professor Handel is probably not sucking the information out of your head the longer you stay at the review session. It's that students who stay at the review session longer are probably less comfortable with the exam material. So they're hoping they're going to get additional information by staying longer. Whereas students who feel comfortable with the material leave early because they feel like they've already mastered all of that information. Be careful about studies that suggest causal relationships. Many newspaper articles cite correlational studies, but suggest that there's a causal link, like, for example, between diet beverages and heart attack risk, or between U.S. spending on science, space, and technology and suicides. Be suspicious. Be skeptical of what you read and hear. If we really want to know about cause and effect, then we need to rely on experimental research. Experimental research exposes subjects to different situations to measure the effect on behavior. In this case, I bring subjects into an environment. For example, I want to know whether or not diet beverages actually does have an effect on your heart attack risk. This is where I would actually be able to test this idea. So I'm going to bring in a group of participants, and I'm going to bring them into a lab, and I'm going to feed them only diet soda, no other liquids. They're going to get 2 liters of diet soda a day. But then I need a comparison group, what we sometimes call a control group. So they're going to get water, 2 liters of water during the day. So I've got 2 groups, and I'm going to measure their heart attack risk. But it could be any kind of variable you're interested in: exam performance, suicides, impulse control or aggression, you name it. So in the example with diet beverages, my diet beverage consumption, whether you get diet beverages or you get water, is my independent variable, which is often abbreviated IV. This is the variable that's manipulated by the researcher. I take a group of participants and I assign them either to my diet beverage or my water group. But then I need to measure a dependent variable, which is often abbreviated DV. The dependent variable is the variable that I think is going to be changed because of exposure to the independent variable. I think that participants who are exposed to diet beverages are going to change in their heart attack risk when compared to participants who are exposed to water. In an experimental research, I can remove the effect of any other confounding variables by controlling the environment. So if I'm worried that it's not just diet beverage consumption that alters heart attack risk, but there's other factors like how much protein or saturated fat you're consuming, how much exercise you get, I can control all of these things. In my laboratory study, I'm going to make sure that all of my participants have a treadmill that they have to walk on 30 minutes a day, 7 days a week, so they all get the same amount of exercise. The treadmill will not let them exercise more, and it does not let them exercise less. In addition, I'm also going to feed them the same standardized diet, so they're all eating the exact same things. I'm also going to make sure that, because genetics might matter, I'm going to make sure that they're all clones of one another. That way, that their genes for heart attack risk don't interfere with my findings. So I've cloned a bunch of people. I brought them into a lab that doesn't have stress, that doesn't have a job they have to worry about. It just has a treadmill and some food, and then the diet beverages or the water they're going to consume all day. Now, that may seem weird and a little bit harsh, but in fact, actually, that is how we set up rat studies all the time. Rat studies are set up in a standardized environment. They're all housed socially together in groups of 4, so they get social time. They all have a running wheel to run on. They all get rat chow. And then basically, if we want to do a study about diet beverages in rats, we just manipulate how much chemical they're exposed to, whether it's water or some other chemical that's put into the water. And rats they're not clones of one another, but they're pretty close. We've basically had these inbred rat lines that have been like this for more than 50 years. So they're almost as close to clones as you could get. And you can order them as clones if you wanted. Now, one of the problems with experimental research is that sometimes your artificial lab study doesn't look anything like the real world. Nobody eats rat chow and runs on a wheel, right? We're not really all clones of one another. We have independence. We get to say what we want to eat. We say how we want to exercise. So sometimes artificial lab studies don't look like the real world, but they do allow us to measure, do diet beverages have an effect on heart attack risk? And by the way, they really don't. There's no evidence to suggest that chemicals in diet sodas are in any way harmful for you. In fact, caffeine that's often in many diet sodas actually can protect you from certain kinds of liver and kidney function failure. The other kind of problem you might have in experimental research is participant bias. In participant bias, this is where your participants are somehow aware of what you're trying to test, and either they change their answers because they want you to get the finding you're looking for, right? Participants really often want to help. So to avoid this problem, you don't tell them what group they're in. So I don't tell my participants whether they're in the diet soda group or the water group. But now you can see the problem, right? Participants might be able to figure out what group they're in. So what you might want to do as a control instead is to have a diet soda group and then a non-diet soda group, right? So at least the taste is more similar. The other problem, though, is not just that your participants might be biased, but actually your experimenter could be biased. Remember, experimenters, either intentionally or unintentionally, might ask questions in ways that bias the responses of your participants. So if you were doing a study on depression and your interviewer was asking participants who were on a new drug whether or not they feel better, the experimenter's attitude or body language or other factors might unintentionally change the answers that participants give if they're in the new experimental drug condition versus a placebo or sugar pill condition. So we can use what's called a double-blind procedure. In a double-blind procedure, both the participants are not told what group they're in, and the experimenter who's doing the interviews is also not told. Now, there is a person who knows, right? There's usually a head of the research project who knows which participants received which treatment, but that person who's the head of the project is not necessarily doing the interviewing or the data collection, so they're not altering the results. The last thing we need to talk about are the principles that make research happen. These ethical principles really came about because of medical research that was happening during World War II in Nazi Germany. There were many studies on live human subjects that we found out about in the 1940s and 1950s. So nowadays we have a set of medical principles that tell us how research should happen. And these apply both for medical research as well as psychological and any other kind of research involving humans. The general principles are we must minimize the risk to participants. You must not cause any harm to them. If there is harm, the benefits of that harm, right, the research findings, the benefits of those research findings must outweigh the risks to the participants. Every participant must be able to give informed consent to participate. They have to know what's going to happen to them. You must talk to them about what the procedure is. And that means if you're going to deceive them, right, you first of all should avoid deception if possible. And most studies these days don't use deception. But if you are going to use some deception, you must give them some idea about what the possibilities are. So, if you're in an experimental drug trial, you as a researcher must tell all participants what groups they might be in. If you're testing out a new drug for depression and one of your treatments is a placebo pill, you must tell your participants legally in the US that they might be receiving a placebo. That way, if something's happening to them, if their symptoms are getting worse, if they're contemplating suicide, they can figure out, oh, I might have the placebo, I need help. Lastly, you must make sure that all data is anonymous, where no identifying information can be found out about that person, or if there is identifying information, like in a medical record, for example, it's confidential. So that identifying information never goes out. No videos are made of the person, no pictures are published with their identity. All of that should be kept private. Okay, so that wraps up our discussion about the principles in research. If you have any questions, please send me an email.